Are you ready to meet the friendliest sounding planet with the worst attitude? People call Venus Earth's twin, but if you tried to step on it, you'd last about the length of this sentence. Here's what they don't tell you about our bright evening star. It cooks steel, crushes submarines, and rains acid. And somehow, we still keep going back. You've seen Venus even if you didn't know it. That super bright star after sunset or before dawn, that's it. It looks calm. It looks soft. It even glows like a pearl. But behind that soft light is a planet that has ended almost every machine we've ever sent there. We're talking heat hot enough to melt lead. Air so heavy, it feels like the bottom of an ocean. Clouds not of water, but acid. If you ever wanted to know what a slow cooker for robots looks like, Venus is it. So why keep trying? Because Venus answers a big question we care about. How does a planet almost the size of Earth turn into a death trap? If we can read its past, we learn more about our own. We also learn how planets change, how atmospheres run wild, and what to expect when we look for life in other solar systems. And there's another reason. Every time we fight our way through those clouds, we get smarter at building tough machines. Venus has made us better engineers. Let's get clear on the setting. Venus is almost exactly the same size as Earth. If you held both in your hands like apples, you'd say the Venus one feels right. Gravity at the surface is close to ours. It's only a bit lower. But the day is strange. One day on Venus is longer than its year. It takes about 225 Earth days to go around the Sun, but about 243 Earth days to spin once. Even weirder, it spins backwards. On Venus, the Sun would rise in the west and set in the east. If you stood there, please don't. The sky would be a thick, yellow soup. You would not see blue. You would not see the Sunday. You would see light, but no shadows, like being inside a lit fog. Now for the numbers people quote, and the numbers that break your brain. The surface temperature sits around the high 400 Celsius, close to 400 and 7,500 degrees Celsius. That's pizza oven heat, non-stop, day and night, pole to pole. There is no cool morning. The air pressure is about 90 times what you feel at sea level on Earth. Imagine being under nearly a kilometer of ocean, except it's gas, not water. The air is mostly carbon dioxide, and the clouds are loaded with droplets of sulfuric acid. Yes, acid. Umbrella is not the right tool. How does a planet end up like this? The short version is runaway heat. Venus likely had a lot of water early on. Under the harsh sun and with little way to store carbon in rocks, its atmosphere thickened with carbon dioxide. Water got split high up by sunlight into hydrogen and oxygen. The light hydrogen drifted off into space. The more the greenhouse gas built up, the more heat got trapped. More heat means more water loss, and the spiral kept feeding itself. On Earth, plants, oceans, and rocks help lock carbon away. Venus never had that stable loop. Once it tipped, it ran away to the world we see now. That is the big picture, but the details came from hard-won missions. Roll back to the early 1960 seconds. The United States launched Mariner 2. It flew by Venus in 1962 and took our first good vital signs. That little probe measured microwave and infrared signals and found the planet was hot everywhere. Not a hotspot here or there. It was a global oven. That single fact pushed people to understand the greenhouse effect in space, not just in a lab. Venus made the idea real. Then came the Soviet Venera program. These were tanks with parachutes. They looked more like deep-sea spheres than spaceships. Venera 4 was the first to sample the atmosphere directly. Later, in 1970, Venera 7 became the first probe to pull off a soft landing on another planet's surface and send data back. It didn't last long, but it proved a point. If you make a lander strong enough, you can touch Venus. In 1975, Venera 9 sent back the first photos from the surface of another planet. Think about that. A robot fell through acid clouds, slammed into a furnace, sat under crushing weight, and still managed to snap a picture of a bleak, rock-strewn plain. Later, Venera landers, like Venera 13, recorded color images and even the sounds of the wind before the heat killed them. Each one survived minutes to a couple of hours. That's all you get down there. A quick, painful window. But in those minutes, they changed history. While the Soviet machines were wrestling with the ground, NASA tried a different angle. see through the clouds from orbit. The Magellan spacecraft reached Venus in 1990. Those clouds are thick and block normal cameras, so Magellan used radar. It pinged the surface with radio waves and built a map out of the echoes. The result is still one of the greatest maps we've made of any world. It showed giant plains of lava, spreading like frozen seas. It showed shield volcanoes, pancake domes, and weird ring-like features called coronae. It showed cracks and ridges that stretched for thousands of kilometers. And it hinted at something huge. Most of the surface looks young. Not yesterday young, but not as old as the Moon or Mercury, which keep scars for billions of years. Venus looks like it was resurfaced, wiped clean hundreds of millions of years ago. The leading idea is that heat built up inside. The crust couldn't let it out in the usual way. And then, in bursts or in a global spasm, the planet spilled lava and reset the clock. If the ground is tough to touch, the air is the easier target. The European Space Agency sent Venus Express in 2006. It orbited for years, watching the atmosphere move, glow, and change. It saw a huge double-eyed vortex spinning at the South Pole, like a giant storm that never quite ends. It traced how the air superrotates winds high above move around the planet much faster than the planet spins, whipping around in a few days. It also saw hints of hotspots on the surface and spikes in certain gases that come and go. Those things point to active volcanism, which would mean Venus is not dead. It is venting now. In 2015, Japan's Akatsuki finally grabbed orbit after a tough start, and has been tracking clouds and weather patterns too, adding to the story of a supercharged, fast-moving sky. All these missions faced the same core problem. Venus fights back. Heat, pressure, and chemistry team up to ruin electronics and melt seals. A normal lander with normal parts will die in minutes. Engineers responded with thick walls, high-pressure hulls, special valves, and cooling systems, but even the strongest shell only buys time. That is why modern Venus plans are so bold. We test new materials. We dream about landers cooled by phase change blocks, where ice inside absorbs heat as it melts. We test electronics that can run at 500 degrees Celsius, made from wide bandgap materials like silicon carbide, so you don't need a fridge. We plan balloons that float up high in the cloud deck, where temperatures are closer to Earth's and pressure is mild. Up there, a platform could live for months and sniff the chemistry, watch the winds, and even send small probes down to taste the lower layers. Let's go back to the surface story, because it's more than just a lot of lava. Magellan's radar revealed features with names that sound like a fantasy map. Aphrodite Terra, Ishtar Terra, Lakshmi Planum. These are the highlands and plains. There are blocks of old, crumpled terrain called tesserae. If the resurfacing model is right, these tesserae may be the last ancient pieces that survived the floods of lava. Coronae are another Venus special, ring-shaped features a few hundred kilometers across, linked to hot blobs rising from the mantle. There are also pancake domes, wide, flat volcanoes made from thick lava, and long canyons carved by flowing lava rivers. You can follow some of those channels for hundreds of kilometers, like frozen highways that once glowed red. One question everyone asks: is there lightning? The short answer is we see signs, but it's hard to be sure through all that cloud and static. Some missions have heard radio bursts that match lightning. Others have seen flashes. If there is lightning, it would feed the chemistry of the sky, creating odd molecules that form and break apart. Speaking of chemistry, those clouds are not water clouds. They're mainly sulfuric acid droplets in a mix of gases with a little water, a little sulfur dioxide, and other trace stuff. The middle cloud layer, around 50 to 60 kilometers up, is the most human-friendly place on the entire planet. Not friendly, just less awful. There, the temperature and pressure are close to Earth levels, even if the acid is not. That's one reason people bring up the idea of floating labs, or even floating cities, in science fiction, and sometimes in serious studies. If you coat or neutralize the acid, a balloon could ride that layer and watch the planet from inside its own sky. Now, let's talk about the twin label. Size and gravity? Yes. But spin, air, and water make all the difference. Earth has plate tectonics. Our crust slides, dives, and builds ranges. That movement helps cycle carbon between air, oceans, and rocks. Venus, as far as we can tell, lacks active plate tectonics today. Its crust seems to flex, crack, and overturn in other ways. Without plates dragging carbon into the mantle and fresh rock reacting with CO2 at the surface, the air keeps its carbon and locks in the heat. Earth also has a magnetic field built by a churning liquid core. That field shields our upper air from the solar wind. Venus has no strong global magnetic field today. Its upper atmosphere interacts with the solar wind in a different way, forming an induced magnetosphere. That means its air can be stripped at the top, atom by atom, over long times. A mix of all these things spin, air, water, plates, field, made two twins, live very different lives. Another thing that keeps coming up, how young is the surface really? When we say young, we mean on average, maybe a few 100 million years old. Crater counts support this. Venus has very few impact craters compared to Mercury or the Moon. And the craters it does have look fresh and spread fairly evenly, which suggests a big resurfacing episode, or repeated bursts rather than slow, Earth-like weathering. If resurfacing came in pulses, that changes how the air and ground talk to each other over time. A burst of volcanism would send gases up fast, thickening the sky and maybe shifting the climate. If the bursts are still happening, that's good news for scientists, because it means the planet is active and we can catch it in the act. We also use Venus as a tool. Spacecraft swing by it to steal or give away speed. It's a great place for gravity assists because it's close to the Sun and massive enough to bend paths a lot. Probes headed to Mercury, like Bepi Colombo, have dipped past Venus to shave off speed and fall inward. The Parker Solar Probe has used Venus multiple times to drop closer to the Sun for those record-breaking, high-heat dives. Each flyby gives us bonus data, quick snapshots of the clouds, fields, and particles. So what happened with life on Venus? You might have heard headlines about a strange gas called phosphine, which on Earth is often linked to life. A few years back, a team reported signs of phosphine in the Venus clouds. It sparked a loud debate. Some follow-up studies said the signal could be noise or could be explained by other gases or instrument quirks. Others looked for different ways to make phosphine without life. As of now, there's no solid proof of life in those clouds. But the whole debate did something useful. It pushed people to think harder about how we search for life signs in harsh places and how easy it is to fool ourselves. It also bumped Venus up the mission priority list. If there is a weird, out-of-balance chemistry up there, we want better tools to measure it directly. Let's fold the story back to the early missions, because there's a lesson there about trying, failing, and trying again. The first probes that aimed for Venus in the late 1950 seconds and early 1960 seconds failed a lot. Rockets blew up, signals died, heat smashed gear. But each failure taught teams how to pack a probe for the worst day of its life. When Venera 7 touched down and whispered data for a bit over 20 minutes, it handed scientists a gift, a reading from the hell we had only imagined. Venera 9's black and white images of rocks sitting under a heavy sky were simple and raw, but they were the first time human eyes saw the ground of another planet through a camera we built. Magellan's radar maps turned cloudy mystery into a place with shapes we can name. Venus Express and Akatsuki turned static oven into a windy, swirling, living sky. Piece by piece, the planet went from a bright dot to a world with a story. Now imagine building the next lander. Step 1. Electronics that don't break at 500 degrees Celsius. Standard chips die fast. Engineers test special parts that keep working when solder melts. Step 2. Seals and cables that don't outgas or soften. Polymers fail, so you move to metals and ceramics. Step 3. Cooling. You can carry blocks of material that absorb heat as they melt, buying you an hour or two. You can isolate your brain in a pressure sphere and accept that it's a timed mission. Step 4. Instruments. What do you spend your minutes on? Do you scoop soil? Do you drill a few centimeters? Do you sniff gases for volcano signs? Do you listen for quakes? All of that has to fit into a small, heavy, insanely tough package that lands blind through clouds on a surface we've mapped by radar but never seen clearly. It's like trying to drop a safe on a specific street in a smoke-filled city. open it for a minute, and read 3 books before the safe melts. That is why some of the most exciting ideas pick the cloud layer at 50 to 60 kilometers up. Up there, the pressure is like Earth's. The temperature is like a hot day on a tropical beach. Yes, the acid makes it ugly, but we can design coatings and filters. A balloon could drift around the planet in a few days and circle it over and over, watching the clouds move, tracking storm waves, measuring how sunlight breaks apart molecules and how they form again. You could even dangle small probes that dip down a few kilometers and then reel them back up. From that vantage point, you can study how the planet loses gases to space at the top and how it cooks new gases at the bottom. You can hunt for weird molecules, not because you expect life, but because any odd pattern tells you how the chemistry and physics play together. Let's spend a moment on the winds, because they are a big part of why Venus looks the way it does. The planet spins slowly, but the winds at the cloud tops roar. They circle the globe in 4 to 5 Earth days. That superrotation isn't simple to explain. Heat comes in from the sun, heat leaves as infrared light, and the air organizes itself into a global machine that runs on that energy difference. Waves move energy and momentum around. Some waves start near the surface, some start higher up. The result is a planet with a lazy spin but a fast sky, with giant, standing whirlpools at the poles. If you lived in a balloon city up there, your weather report would be wild. Constant winds, fast sunrises and sunsets, and endless sheets of cloud in every direction. We should talk about why Venus matters for exoplanets too. When we look at other stars and see Earth-sized planets close to them, we don't know if those worlds are little Earths or little Venuses. The difference might be where they started, how much water they had, how close they sit to their star, or pure luck. If we can read Venus's story right, we get a template for this is what a runaway greenhouse looks like from far away. The thick CO2 air, the acid clouds, the huge day-night temperature balance at cloud height, the lack of a clear surface in visible light. These are signs we can try to match in the light coming from exoplanets. That helps us sort the could-be-friendly from the probably-not a lot faster. You might be wondering about quakes. Does Venus shake? We don't have a network of seismometers there, but we have clues. Some features look like they formed from ground moving. Some studies of small changes in the atmosphere suggest waves that could be linked to quakes. If we can set a small package on the surface and have it listen for an hour, we might catch a rumble. Even a short quake record would tell us about the crust and the mantle right below the lander. And if we put a few landers down in different places, tough, but not impossible, we could start doing real internal mapping, like we've done on Mars with InSight and on the Moon with old Apollo gear. There's also the question of water today. The lower atmosphere is dry, but the higher clouds hold a little water. Venus Express measured the ratio of heavy water to normal water in the air and found more heavy water than Earth has. That supports the lost water story. Lighter hydrogen escapes more easily, leaving behind a higher share of heavy hydrogen. It's like the fingerprint of an ancient ocean that boiled away. If that's true, we're not just looking at a hot world, we're looking at a graveyard of a sea. Let's not skip the human angle. Venus taught us humility. Early on, many people thought the clouds meant rain, and maybe even a swamp below. Science fiction loved that idea. Jungles, monsters, a young Earth in a veil. The truth was the opposite. The first solid temperature data was a punch in the gut. Pictures from the ground were bleak. The clouds were not a soft blanket, they were a chemical hazard. It's easy to be disappointed, but what we got instead is more important. We got a clear, scary example of how fast a world can flip when certain feedbacks run wild. We got a natural lab where you can see greenhouse physics scaled up to the max. That doesn't mean Earth will become Venus. The planets have different stories, and we have oceans, a carbon cycle, and a magnetic shield. But Venus shows the stakes when balance breaks. You might be thinking, if it's that awful, why not ignore it and go to Mars? We do go to Mars, a lot. But space is not a one-planet game. Each world answers different questions. Mars asks about past water and ancient life. Venus asks about climate, geology without plates, and how planets near the inside edge of the habitable zone behave. It also sits in a spot that helps us reach other targets, so even our side trips past it add value. And to be blunt, hard problems push tech forward. Surviving Venus's heat gives us high-temp electronics, better seals, and new materials. Those help on Earth too, in engines, factories, and harsh environments. So, what should you picture when you hear Venus mission in the next few years? Picture a cloud-level balloon tracing fast loops around the planet, sending back stunning data on winds and chemistry. Picture a small, brutal lander dropping fast, transmitting everything it can in an hour before the heat wins. Picture an orbiter with a modern radar that maps the surface at higher resolution and watches for changes over time, hotspots that flicker, landslides that shift, fresh lava that wasn't there a year before. Picture new instruments tuned to sniff out rare gases that reveal what the interior is doing. Picture, maybe down the line, a fleet mission, an orbiter, a balloon, and a lander all at once, talking to each other and giving a full layered view from space to ground. When you strip the romance away, Venus is simple. It is a planet that shows what happens when a thick CO2 blanket keeps piling on. But when you look closer, it's full of puzzles. Why does the air spin so fast when the ground spins so slow? How exactly did the resurfacing happen, one global flush or many bursts? Is the planet still belching out new lava today? How is the air being lost to space, molecule by molecule? Are there chemical cycles in the clouds we don't understand yet? Each puzzle is a hook. Each answer is a step toward reading other worlds better. Let's pull back and tell the story straight. First, we learned Venus is hot. Then we learned it's hot everywhere. Then we touched down and saw rocks under a dead, heavy sky. Then we mapped the whole surface and saw the scars of fire. Then we watched the clouds and found deep, strange weather. Now we are building the next round of tools to go back. And while all that happens, Venus helps us in another way. It bends our paths so we can reach Mercury faster and fall closer to the Sunday. Even when we're not studying it, we lean on it. One last thought about that twin label. It's tempting to think, same size, same story. But Venus is a warning that small starting differences can lead to huge endings. A bit closer to the Sunday, a different spin, a different water story, no strong magnetic field, no plate tectonics. Put those together over billions of years, and you don't get a blue marble. You get a pressure cooker in the sky. When we search the galaxy for other Earths, we have to keep that in mind. The light curve of a far-off planet won't tell us if it's a field of flowers or a sea of acid. We need more clues, better models, and planets like Venus to teach us what to look for. If you've ever looked up at that bright evening light and felt calm, that's fair. It is calm from here, but now you know the truth behind the glow. Venus is the harshest world we've tried to visit, and it keeps daring us to try again. And we will, not because we love pain, but because this is how we learn what a planet can be and what ours is not.